Welcome. In this explainer, we are going to tackle one of the most powerful tools in all of calculus, L'Hopital's rule. It's this really elegant shortcut that can solve some of the absolute trickiest limits you will ever come across.
So here's our game plan. We'll start by talking about the problem of fighting limits. You know what happens when functions are racing to zero or infinity. Then, we'll introduce the solution, L'Hopital's rule, and even peek under the hood a bit to see why it works. After that, we'll put it to the test with a bunch of examples and wrap it all up with the key takeaways.
So let's just set the stage here with a question. I want you to imagine you've got a fraction, and as you get closer and closer to some value, the top part is racing towards zero. But at the exact same time, the bottom part is also racing towards zero. So who wins? Does the whole thing just become zero? Or maybe infinity? Or something else? It's like a mathematical tug of war. Okay, let's get into our first section and see how we actually describe this conflict. This is what mathematicians call the problem of indeterminate forms. So the most important thing to get is that when your limit calculation spits out something like 0 over 0 or infinity over infinity, it's not a dead end. It's called an indeterminate form. And all that means is, well, the answer isn't determined yet. It's basically a signal from the problem telling you, hey, you need a more powerful tool here. Now this slide, this is absolutely critical. On the left, you've got our indeterminate forms. These are the green light, your permission slip to use L'Hopital's rule. But on the right are what we call determinate forms, like infinity divided by 0, where the answer is already super clear. Trying to use the rule here is probably one of the biggest mistakes students make. So you've really got to know the difference. And that brings us to the hero of our story. So what is this special tool that just cuts right through all that confusion? Well, it's a super powerful shortcut called L'Hopital's rule. And here it is. The rule itself is just beautifully simple. If you're stuck with a 0 over 0 or infinity over infinity problem, all you have to do is take the derivative of the top function and the derivative of the bottom function separately, and then try the limit again with that new fraction. It's such an elegant fix to that fighting limits problem.
But hold on, why is this even allowed? I mean, it almost feels like cheating, right? Let's take a quick look at the really cool concept that makes this whole thing mathematically sound.
The entire reason this works rests on this one single powerful idea from calculus. It's sometimes called local linearity. All it means is that if you take any smooth curve and you zoom in really close at any single point, it starts to look exactly like a straight line, which is, of course, its tangent line at that point. And here's the magic connection. Right at that point where our functions are creating that indeterminate form, they behave just like their tangent lines. And since the slope of a tangent line is the derivative, the ratio of the original functions becomes basically the same as the ratio of their slopes. And that's why we're allowed to just swap the functions for their derivatives. Pretty cool, right? All right, theory is great, but let's actually see this thing in action. It's time to solve some real problems, from the pretty straightforward to the downright tricky. Let's kick things off with a classic race to infinity, the natural log of x versus just x. Step 1, always check the form. As x gets huge, both of these functions go to infinity. So we've got infinity over infinity. That's our green light. Step 2, differentiate. Derivative of ln x is 1 over x, and the derivative of x is just 1. So our new limit is now the limit of 1 over x divided by 1. As x heads to infinity, 1 over x heads straight to 0. And that's our answer, 0. Okay, let's level up a bit. What happens if you apply the rule once and you just get another indeterminate form? Let's check out an example where we have to use it twice. So let's look at this limit, 1 minus cosine of x all over x squared as x goes to 0. Plug in 0, and sure enough, you get 0 over 0. Great, let's apply the rule. The derivative of the top is sine of x. The bottom is 2x. Our new limit is sine of x over 2x. But hang on, if we plug in 0 now, we get 0 over 0 again. No big deal. The key is you can just apply the rule a second time. So the derivative of sine of x is cosine of x, and the derivative of 2x is 2. Now our limit is cosine of x over 2. We plug in 0, we get cosine of 0 over 2, which is just a nice, clean 1/2. Done. All right, now for a real challenge. What if the problem doesn't even look like a fraction? Let's tackle an indeterminate power, the famous 1 to the infinity form. This famous limit is actually the definition of the number e, and it's in that weird indeterminate power form, 1 to the infinity. To crack this, we gotta use a clever logarithm trick. First, we just set the whole limit equal to y. Then we take the natural log of both sides. This lets us use log rules to bring that exponent x down in front. Now the problem is an infinity times 0 form, which we can rearrange into a fraction. Finally, it's in the 0 over 0 form, so we can use L'Hopital's rule. The limit works out to be 1. But, and this is important, remember, that's the limit of ln of y. So if the natural log of our answer is 1, our original answer y has to be e. Let's do one more type. How about indeterminate subtraction, like infinity minus infinity? This one needs some good old school algebra before we can even think about using our fancy calculus shortcut. So for this limit, 1 over x minus 1 over sine x, we've got an infinity minus infinity situation. Our first move here is algebra, not calculus. We have to find a common denominator and combine these into a single fraction. Now it's in the 0 over 0 form, and we can finally unleash L'Hopital's rule. And for this one, you actually have to apply it twice. But after that second round, the limit works out to be 0. This is a perfect example of how your first job is always to get the problem into the right form.
All right, let's bring it all home and summarize everything into a simple checklist. Think of these as the rules of engagement you need to remember to get L'Hopital's rule right every single time. This checklist is honestly your key to success because pretty much every mistake comes from breaking one of these rules. First, always, always, always check for the 0 over 0 or infinity over infinity form. Second, you differentiate the top and bottom separately. I'm going to say it again. This is not the quotient rule. Third, be ready to apply the rule more than once. Fourth, use algebra or logs if you have to create that fraction form. And last but not least, if the limit is already determinate, just stop. The rule doesn't apply. So I'll just leave you with this thought. This rule really opens up a whole new class of problems. Now that you have this amazing shortcut in your toolbox, which of those complex, intimidating limits, the ones you might have just skipped before, are you now ready to go back and handle?